Hi everyone, so we're going to have a look at this pulleys and friction question from yesterday's lesson. And I'm going to go through this step by step, so hopefully you've got this question in front of you and you've had a go at it. Can you make sure then that you check through your answer, and if you need to correct it or get a correct solution into your notes, make sure you do that during today's lesson. Okay, so the first thing I'm going to do is I'm going to add to this diagram any information that we're given here and any forces that aren't already on here. Okay. So we've got a block of wood, mass 0.5 kilograms. So we've got our 0.5 kilograms shown here. I'm just going to add my weight onto that, vertically down, so that's 0.5 G. It's on a rough horizontal table, and again with these questions, my advice is to sort of circle these things that are important. It's rough, so that means there's going to be friction opposing the motion. And don't forget, friction always acts in the opposite direction to the motion in the system. Okay, so we've got some friction going on here. So this system, when it's released from rest, is going to go this way, caused by this downward force here, by the weight of this particle. So my friction is going to be acting against the motion. So I'm going to put my friction on here, acting at A. So there's my friction. Okay. We've also got then the other ends of this string is attached to this ball, mass 0.8 kilograms. So again, I'm going to put my weight on my diagram straight away. And this, it tells us, is hanging freely. So this isn't in contact with any of the surfaces here. This is just hanging freely over the edge of this surface. The coefficient of friction is mu, and we're asked to find that later in the question. And the system is released from rest with the string taut. There's going to be tension in this string, obviously, as this starts to move. After release, B moves downward, descends a distance of 0.4 metres in 0.5 seconds. So this is shouting at me that there's going to be suvat involved here. We've got displacement, we've got time, so we'll have a little look at that as well. Modelling A and B as particles, calculate, and then we're going to do this question. So I'm going to cover over the question here, and I'm going to have a look at going through this answer, keeping my diagram here, and hopefully you can go through this step by step. So we're asked to find, first of all, in part A, the acceleration. Well, before I start to do that, I'm actually just going to have a look at my resultant force equations here, just to see what's going on, to get all my information down, and then hopefully that will help me with some parts of this question. And as I say, feels to me like suvat's going to be involved here as well. Okay, so let's have a look at what else we need on this. We need a reaction, normal reaction force here. And we need our tension in the string, the tension acting to pull this one around the table that way and stopping this one just free falling down. And there's my tension. And it's the same tension all the way through, because it tells us here that it's a light, inextensible string. So actually we're asked about this at the last 1 mark of the question. But what does that mean? It means the tension throughout this system, throughout the string, is constant. It's the same string. It's inextensible. So that means that the acceleration for the full system is going to be the same for both particles A and B. The whole system is moving with the same acceleration. So we're going to be accelerating in that direction here and accelerating with the same acceleration downwards there. So A is going to move across to the right. B is going to move downwards with the same acceleration. Okay, let me cover that over. Let's start this question. And part A is asking us for the acceleration. But as I say, before I do that, I'm just going to actually look at resultant forces for A and for B, just so I've got all my information down. I may not need this straight away, but I'm sure I'm going to need it throughout the question. Okay, so let's look at particle A first of all. We've got things happening horizontally and we've got things happening vertically. Okay, and the overall motion is to the right. So if I look horizontally first of all and take to the right positive, so I'm going to be looking horizontally here. What do I know? I know resultant force equals MA. And the resultant force here is going to be T minus my friction, and that's going to be equal to mass 0.5 times A. So there's one equation sorted there. Let's now have a look at vertically as well. So vertically, what's happening? I'm just going to take up as positive. Well, vertically, here. And you don't need to do this in this order, but I'm just going to go through step by step, getting all our resultant force equations down. So vertically, there's no motion here, so there's going to be no resultant force. Okay, so nothing's happening here, up equals down. If I'm going to take up as positive, then R minus 0.5 G is 0. So R is equal to 0.5 G. So I'm working through this and I've just got some information down. I haven't answered anything yet. Let's have a look at B. B, all that's happening is vertical motion downwards. So again with B, if I look at taking down as positive here, because that's the direction of motion, then downwards here, 0.8 G minus the tension, slowing this thing, stopping it just free falling. And that's going to be equal to mass times acceleration here, which is 0.8 times A. Okay. My friction's been overcome, so the other thing I can put in here now, my friction must be equal to F max, and I've got my 0.5 G here as well, so let's have a look at that. I'm just going to do that in red so we can see what's happening. So my friction is definitely going to be F max because it's being overcome. This block is moving, so that's equal to mu R. So that, my friction, whatever this is equal to mu R, so that's going to be 0.5 G times mu there. Now looking at all of these, I've got too many unknowns here to do anything with by the looks of it, because I could put my friction in here, but it's still got mu in that I don't know. My tension I don't know. My acceleration I don't know. So I've got 3 unknowns, but only 2 equations to work with. And so to answer, I've got some stuff set up here, but to answer part A, the acceleration, I haven't got enough information. So I'm now going to have to use some SUVAT here to get some information. And we said before, we've got a displacement, we've got a time, so we should hopefully be able to set up an equation here. So let's have a little look at doing a bit of SUVAT here as well. I'm just going to move this up a second. So let's consider some SUVAT here. So let's just see what we're told and what we want. We're told down here, time is 0.5. It's descended a distance of 0.4. So we're looking at B here. Descended a distance of 0.4, so displacement is 0.4. Taken down as positive here. My displacement downwards is 0.4. My time is 0.5 seconds. What else do I know? Well, the other thing I know here, and again, maybe we should underline this, is it says the system is released from rest. So look, there it is there, from rest. From rest always means that the velocity then at rest is 0. So if it's released from rest, then U is going to be equal to 0. My initial velocity is 0. I'm not bothered about V here. I want to know what A is. So I've got enough information now to use my SUVAT equation, S equals UT plus a half AT squared. Let's substitute in what we know. 0.4. U is 0, so nothing times T is still nothing, plus a half, A we're trying to find, T is 0.5, so 0.5 squared. Sorting this out then, rearranging, you should end up with the acceleration is 3.2 metres per second squared. Okay, so that's part A done there. These other bits though, we've now set up, we should be able to use them to answer these other parts of the question. And if you hadn't done those first, if you'd gone straight to SUVAT, that's absolutely fine. But the fact that I've now set these up means that I should be able to answer these questions, hopefully without too much difficulty. Okay, so let's have a look now at doing this. Okay, so looking now at part B, we're asked to find the tension. Well, I know the acceleration now, so that can go in here. So this one will tell me the tension here straight away. So let's have a look at that. I'm just going to move that across a bit. Let's do part B over here so we don't run out of paper. So part B here, 0.8 G minus tension is 0.8 times my 3.2. Rearranging, sorting that out. I'll let you do that if you haven't already. You should get 5.28 newtons. Okay, so there we go for part B. And obviously, if I hadn't set this up at the beginning, I'd be setting those resultant force equations up down here. So that's sorted that one for me. And the fact of that, sometimes people go, why is that worth 4? It's worth 4 because you had to set this stuff up here to be able to get to here. Okay, part C, the value of mu. Well, this side then, the stuff I've done with resultant force here has got friction involved. Friction's got mu in it. So I'm going to use this side now to find out the coefficient of friction. So part C, looking at A then, what have we got? We've got tension. We've worked that out now. So let me just write that down again, down here. We've got the tension is 5.28, and that's the same for A and for B, we've said already, because it's an inextensible string. We've got the friction is F max, which is this, so this is 0.5 G times mu. And then I've got my 0.5 times my acceleration, and again, because this is an inextensible string attached to two pulleys, the acceleration is the same for A and for B, so that can go in there. If we sort this out, play around with this, solve this equation, you should end up with mu equals 0.75107, so 0.751 to 3SF. Okay, so that should have come from rearranging this equation. The only thing we just need to make sure we've written down then at the end is we talked about this earlier, part D, state how you've used the information that the string is inextensible. Well, how have we used that? So for part D, that means that the tension is constant throughout the string. And it means that the acceleration is the same for the whole system. So i.e. for A and for B. Okay, so a statement here about how we've used that, and this is really important, isn't it, with the acceleration being the same. We used that right from the very start of this to sort out that question. So hopefully you've had a good go at that question yourself yesterday. Have a look at it, get it marked. If you've made some errors or you were unsure, then make sure you get a corrected version in your notes, please.